start off with Alex.
Good evening, everybody. How are you guys? Doing good? That's good. Lots of energy. So my name is Alexander Eppening. I'm a professor in computer science at the University of Colorado, but I brought a couple of colleagues also from HEG and from the School of Education. I want to talk about a problem. Mission accomplished, really. In 1995, in our research, we started very early on. As you can see, this is almost 20 years ago. We actually pioneered this idea of drag and drop programming. And at the time, and even now, people think, oh, mission is accomplished, right? Now programming has become trivial. Everybody can do it, right? But I want to give you one analogy. If I give you something like Word, a word processor, and say, let's do spell checking, and then I say, now that you have spell checking, which is basically the equivalent of drag and drop programming because you can make no syntactic error, go and write a best-selling novel. How hard could it possibly be, right? Because I gave you all the tools you need. So that's not quite true. Mission not quite accomplished, right? So I think, this event is fantastic. I completely enjoy it. But I want to at least give you a sense of the statistics here. For instance, for every student that you find at this hackathon tonight, that's roughly 80, for everyone, there's 360 students not being here. Right? So that sort of gives a sense of ratio. So that's not good. So what we started to do in our research, we actually started to realize that we really need to get this computer science education and these kinds of tools into schools. So we need to shift from after-school programs to in-school programs. And in 2007, we started with support by the National Science Foundation, a new kind of curriculum called the Skills of Game Design. And I want to just very quickly give you a sense of what are the core components of this idea of skills of game design. The first one is exposure. Right? This idea of try the vegetable once may not always result in good outcomes, but we basically found that if we have this idea of sneaking a one-week game design activity in between keyboarding and other exciting topics such as PowerPointing into a so-called, in some cases, forced elective, interesting concept, I didn't make that up, then it actually turns out every student will be exposed to this. Now, if you look at the results, we've actually running at the moment the largest U.S. middle school study. We have over 10,000 students, and that's in inner city schools, remote, rural, and Native American communities. And when I say some of these schools are tough, we're talking about schools at the middle school level where some of our teachers got beaten up by the students. That's a pretty tough environment. But if you do that, in some of these schools, we have 350 students per year per school. Right? That's amazing. These are enormous numbers. And the percentage, we have almost 50% girls, and we also have many students that are underrepresented. These are not the self-elected students. We have now exposure from north, south, east to west, and we have expanded to other countries. So for instance, here is Brazil. Now let's look at motivation. That's the second component of our strategy. Start with simple 2D games that everybody can build in a couple of hours. And by that I mean a complete game. I don't mean, draw a button onto the screen, label it fart, and guess what happens when you press it. That is not a game. That may be very entertaining, but has very little to do with computer science education. And so from that, you can move on to make much more sophisticated kinds of games like this one, where you have advanced AI concepts that require advanced math. But the kids want to do it because they say, I need to make this game. I need to have this AI. I want to do this math. And so the results in terms of motivation are that we have a very high percentage of boys and girls who want to participate and want to continue. And again, these are not the self-selected students, right? These are not after-school programs. These are all the students. And we have also started to lower even the level beyond middle school, so we even have some elementary schools that have participated. Third component, education. So when you have excited kids, what is it that they're actually learning, right? I mean, we really need to know, because schools are not here for the business of entertainment. And so one of the best quotes I heard was from one of the instructional technology directors who said, I really like this idea that you motivate the kids, but at one point I want to go into a classroom, I want to ask one of those kids making a game and want to say, now that you can make Space Invaders, can you also make a science simulation? And I thought that's a really clever question, and that should really be a test for us to say, is it really something that we can teach the kids that goes beyond just making games? And so what we have done, without going into details, we can actually measure these skills. So when they make these games, we can actually extract these computational thinking patterns and can track them even over time. And so finally, pedagogy. We have some ideas and hints on what it takes to get more girls excited. But what about an actual theory of promoting participation? Could you really analyze this maybe systematically, look at the data, and actually, now that we have all these schools in all these different places with all these different teachers, and say, when does it work the best, for instance, for the girls? And here's good news. The answer turns out is actually pedagogy, right? So when we actually look at in what schools most of the girls are participating really well, and by that I mean, nearly at basically identical levels between boys and girls. It's the schools where the teachers don't just do direct instruction, right? By direct instruction, I mean, here's a computer science class for you. Do this, enter this, press this button, enter this equation now. Guess what? The girls seem to be significantly less excited than if you do guided discovery. If you explain scenarios and say, now that we make a game like Frogger and the truck is about to hit the frog, how exactly would we be thinking about that? And that seemingly little difference makes all the difference. It gets the girls excited, it gets the boys excited. It's a great thing. And finally, in terms of pedagogy, there's also another thing that we need to be very careful about. Here in this picture, there's essentially this idea of challenges versus skills. How do you go? What kind of trajectory are you going to use? The traditional trajectory is at the bottom, where you just beat the kids over the head with giving them skills and say, here's some interesting stuff for you. Linear algebra, who knows what, can be undergraduate, can be middle school. You beat them over the head to the point where they say, I don't really care about this material. And then finally, when they come to me and take a computer graphics class, I said, I should have paid attention to linear algebra. It actually turns out it is a useful idea, but it's way years too late. So instead, we go up this other kind of trajectory, push them into what we call, the zone of proximal development, push them at their edge of their understanding where they really want to do these things, and they can do these things. And that's the really exciting thing. So with that, I'll like to thank you very much and just give you a couple of more pointers. So if you want to go to the website to look at the curriculum, feel free to contact me, or also here's our Hour of Code activity, which you can just play, and there was a recent article in Wired about our work. Thank you very much.